Okay, so we're going to introduce these SUVAT. We might look at the SUVAT equations, but first we'll just look at what SUVAT is. So we've got you spell SUVAT. That's just a really good way to help you to remember the different variables. So we've got displacement, which is just essentially it just means distance. Okay, so it's distance measured but the difference being is it's the vector version of distance. Excellent. Good. So displacement, if I was moving forwards and I moved forwards 10 meters, then that's the displacement is simply 10 meters. But if I went backwards, then the displacement would be negative 10 meters or whatever. Same with all the other ones. So positive, it means forwards, negative means backwards. So velocity is like speed, but you can go forwards or backwards. And obviously we're looking at a situation in which something might accelerate, so change the speed from a starting velocity or initial velocity to a final velocity. It may be slowing down, it may speed up, or it may stay constant speed. Now, one thing that whenever you look at these kind of problems with these variables, we at GCSE you only really consider constant acceleration. Okay, so the sorry, I'm using the symbols. Sorry, I'm using the units here, not the symbols. The symbols on the left. So these would be the symbols, and over here these are the units. So the unit for acceleration is meter per second squared, and the unit for time is just seconds. So let's think about how we can use these together. Let's imagine we had a graph. So I'm just going to draw a graph. Let's try that again. So let's draw the y-axis and the x-axis. And we're going to do a velocity time graph. Okay. So that's time along the x-axis. In fact, I'm going to just write the word time. And over on the y-axis, I'm going to write velocity, but I'm going to just write it normally and then rotate it. I find that's the best way to do it. Rather than trying to write on the side. So that's velocity. Okay. Now, if we're considering a situation where the acceleration is constant, what we mean is the rate at which the velocity changes is constant, right? That's what acceleration means. It's the rate at which we increase or decrease acceleration, the rate at which acceleration changes. So if you have deceleration would be the word you would use for if acceleration is negative, essentially. So if we're going, so if let's think about an example then. Let's say an object is going forwards at maybe 10 meters per second. In A level, we should write that as meters second to the -1. So it starts off as 10 meters per second, and then after, say, 5 seconds, we notice that it's now moving at maybe 2 meters per second. So it still went forwards the whole time, but the acceleration, the final speed was lower than the initial speed. So the change in velocity, I should use the word velocity, but the change in velocity is actually a negative because it's gone down. So when I say change in, I should really probably say increase in. So the increase in velocity would be negative because it's actually a decrease. Does that make sense? So if I did the triangle V means change in velocity, we would say that's equal to or increase in velocity, which would be equal to the final velocity minus the initial velocity. Now you can see the potential confusion here. Velocity in general is just v, but when we consider two different velocities, we say the final velocity is v and the initial velocity is u, right? So that's and so the change in velocity is going to be v minus u. Now, acceleration is equal to the change in velocity divided by the time it took to change, because we want it's the rate of change in velocity, how quickly the velocity changes, right? Yeah. So we've got, so that's going to end up with being v minus u over t. And that's an equation that you often use at GCSE, and we continue to use at A level, but it just gets rearranged a little bit. So we've got A is equal to v minus u over t, and then we would rearrange that and by multiplying. In fact, do you want to try and rearrange that on a pen and paper? And I want to have it rearranged to say v is equal to something. Yeah, so that, yeah, exactly. AT plus V equals U. Now you'd probably write, the way it would be written would be this, the V is on the left, so, but it's the same thing. So V equals U plus AT. So that would be one of the equations that we might use. So and that's actually one of the SUVAT equations, in fact, and we can call that equation 1. In fact, let's do that, and we'll draw a highlighter. We'll highlight that. That's one of our equations we can become familiar with. Now, what we're going to do next is we're going to take this graph and we're going to imagine if this velocity time graph was describing something starting at an initial velocity u and then speeding up to a final velocity v, how would that be represented on the graph? So if it was, so in other words, we would have it, oops, that's not the right line. Let me just change the type of line. And we'll change the color as well. So basically, yes, it would look something like that, where we have a starting velocity of u and a final velocity of v. Now we can actually demonstrate this on the graph by saying that bit there would be u, and this bit, if we draw a dotted line, would be v. Does that make sense? And this bit down here, because this is how long it took to go from u to v, would be our t, right? Does that make sense? Okay, so we've got it's something is speeding up, going from u to v with constant velocity, constant acceleration. You can see that it's constant acceleration because the slope of the line is constant. So it's so it doesn't get steeper or less steep. It stays the same level of steepness. Now the gradient of the line, which we could draw, which we could measure using a triangle. We won't go into how to do gradients at the moment, but the gradient of the line, in fact, yeah, so let's do the largest gradient like this. Gradient of the line would be the change in the x. So it's going to be the change in the y divided by the change in the x. Okay, so this change in velocity, I'll say, is going to be basically v, all of v minus this u bit. So the length, so this length, if we went from the bottom to the top, it's going to be that length. So this line, if I just use a highlighter for a moment, so the length of that line would be v, and then the length of this little bit, which we want to not include, would be u. So that means that the length of the bit that we do from there to there would be v minus u. Does that make sense? Yeah. So although this is a point, it's also we counted from 0 all the way to v, so that whole height up to v is equal to v, and then from here to there is equal to u. So if we just want to go from there to there, we'd say v minus u, and so the gradient would be equal to v minus u v minus u divided by the change in time. The change in time is equal to t. So over t. And so there, and that's what we've got there. So that's why the gradient is equal to the acceleration. Okay. So that's one useful thing that we can see from this graph now. Another thing we can see is that, what's the next thing we can see? Well, you may or may not know that the area underneath a velocity time graph is equal to the displacement. So let me just write that down in the notes. So the area underneath a velocity time graph is the displacement, and we'll talk about why that is the case in a moment. But I think for now we'll just go, just trust me, it is. So the area underneath this is the displacement, and now we're going to see how we could work some of these things out. So if that's the case, then I can look at this area and I could basically chop it up into a couple of pieces. So this triangle here, this top triangle, and also let's pick a different color. Let's pick a green, this bottom triangle. And those two areas added together would be equal to the displacement according to this sentence. So we'll talk about why the area underneath the velocity time graph is the displacement, but for now, let's just trust that it is. The area of this triangle, sorry, the area of this rectangle is going to be base times height. So the height is u, and the base is t. And the area of this this triangle here is going to be, well, the height of that is, well, the area of a triangle is equal to half the base times the height. Okay, so the area of any triangle, if I had a triangle, doesn't matter actually whether it's a right angle triangle or not, but if I knew the height of this triangle and I knew the base of this triangle, then the area is actually equal to half the base times the height. So the area of this triangle is going to be the same, half the base times the height, and that's going to be equal to, so half times the base, which is t, times the height, which is v minus u, which we worked out a moment ago. Okay? Now, if we look at this thing over here, a is equal, that we looked at earlier on, a is equal to v minus u over t, we can rearrange that and say v minus u is equal to at. Okay? Which means when I said that that half t minus v minus u, first of all, I think it just looks a bit neater if I put the, oh, let's try that again. I think it looks a bit neater if I put the half t over, no, not the half t, just the t over to the other side. And it's going to be convenient in a moment as well, because what I'm going to do, instead of writing v minus u, I'm going to write just at, because v minus u is at that we worked out earlier on. So I'm going to get rid of the v minus u. I'm going to write a t. Now we've got half a times t times t. Well, t times t is t squared. So half t squared. Yeah? So that means the total area underneath this triangle, which I've said is equal to the displacement, is also equal to ut plus half at squared. So our second SUVAT equation is S is equal to ut plus half at squared. Okay? No, but I tend to always write them in the same order just because that is how they're written, and it means I'm more likely to remember them, be familiar with them. So yeah. So if you rearrange, in fact, you do need to rearrange them in many cases. So yes, and just, do you mean like half at plus u? Oh, No, you don't have to know them in any order. In fact, I could be getting the order wrong if there is, in fact, an order. There probably isn't an order. So it's just I'm doing them in this particular. I tend to do them in the same order every time because I've taught SUVAT for a while. So, but yeah. So I'm going to say another one, which I'm not going to go into how it's proven at this point. I'm just going to show you that it's very similar to this one. So, and it's S is equal to Vt minus half AT squared. We wouldn't talk about why that is. You could, if you wanted, a little challenge to try to prove that. It's not too hard once you've seen the other ones, and it's just a manipulation of this one really, with some other bits and bobs. But I won't do that in this video. What we'll do is talk about another situation where you've got. We're going to say that. Let's just draw a little box around this one. So we've got 3 now. What we are going to do as well, though, is we're going to remind ourselves that the equation for kinetic energy is equal to half mv squared. And we're also going to say that if I apply a force against something and I move it a certain distance, or we can say displacement S, then that would be the work done on it. Or it's also equal to the change in energy. And if I'm causing something to increase in velocity, so the kinetic energy, then it can be the change in kinetic energy. So the change in kinetic energy is going to be equal to the initial kinetic energy, EK, let's say EKI. In fact, let's rearrange that now. Let's change that. So I'll start that a little bit again. I'll say that the final kinetic energy, EKF, is going to equal to the initial kinetic energy, EKI, plus the work that's been done on it. Does that make sense? If it has a certain amount of energy already, then the final energy is going to be whatever energy it already has, plus the energy I'm going to give it. Does that make sense? Yeah. Okay. So we can say that that's equal to, we could say delta EK, but let's just say it's FS, because that's going to come into that's going to be useful later on. So yeah, and then we're going to use another equation. We've got lots of equations in this video, in this lesson. So F is equal to MA. Okay. So so this is just Newton's second law. Basically, it just describes that if you apply a certain force to something, then it's written in this way, but it's often understood better if I rearrange it to A is equal to F over M. So the acceleration of any object would be equal to the force applied to it divided by its mass. So if I try to accelerate something very, very heavy, like if I'm pushing a car, eventually the car is going to get faster and faster and faster, but it's going to take a lot longer to get faster if I push the same force to something much lighter, right? So the acceleration is going to be inversely proportional to the mass. So the higher the mass, the lower the acceleration, but also the larger the force, the higher acceleration. So directly proportional to. Anyway, that's a different lesson, really. So we know that kinetic energy is equal to half mv squared. So we're going to now rearrange this equation. Actually, no, let's just rewrite it for now. Let's just rewrite it and keep it the same. So EKF, well, that's going to be equal to half times the mass times the final. So it's the final velocity. So it's going to be V squared. We've got to use V. This V was just the general symbol for velocity. So that's going to be equal to half. So it's initial kinetic energy. So it's half times m again, and this time it's the initial velocity. So times u squared. Okay. Yeah, so it's going to be that plus that, so then plus fs. Now f is ma, so plus m a s. Okay, mass times acceleration times displacement. Okay. So you might have noticed why I wanted to do this now, because we never had, if we go back to the word SUVAT, mass isn't in it. And so I've done all this fancy rearrangement because I can now cancel out the m's. Because I've got m times, all of them are multiplied by m, so I can just cancel, I don't want to delete that as well. I can cancel out these m's. And I've got this, so I've got half times, let's tidy this up now. So I've got half v squared is equal to half u squared plus as. So final step to get to our next SUVAT equation, I'm going to multiply the entire thing by 2. So I've got v squared is equal to u squared plus 2as. Okay. So all these formulae are going to be useful for when we're trying to solve problems with things that are moving at a constant acceleration. So we have to first introduce the equations, and then we're going to try to apply them to different situations. So we've got, one of the things I'm going to introduce, one of the reasons why we have so many different SUVAT equations, and that is because we have in this equation here, if you think of the word SUVAT, S-U-V-A-T, this equation here, this first one, is missing the S. And this one is missing the V. And this one is missing the U. And this one is missing the T. Whoops, it's missing the T. So we just need one equation now, which is missing the A. All of these equations have A in it. And the reason why we want equations that are missing something is because you may not be given that variable. You may not be given the acceleration, for example. They may give you some other things and ask you to work out something, but they don't want you to work out the acceleration, and they don't give you either. So we would need a different equation. So the final equation would be, if we know that something is starting at initial velocity u and finishing at initial velocity v, final velocity v, taking a certain amount of time, we can say that the displacement is equal to basically the average velocity multiplied by the time, right? So if we know that if we take a velocity time graph, let's imagine it wasn't constant velocity. This works for all situations. The velocity is just changing everywhere, right? If we were to find out the average velocity, and let's say it was around about here, we could imagine that's supposed to be flat. We could imagine that it was moving at that speed, that velocity the whole time. That's definitely not the average velocity. I'm going to do it maybe about there. Well, that's probably not quite right either. But anyway, the point is, you could imagine that it was moving at that velocity the whole time, and then say that the area underneath that line is equal to the displacement. And so the displacement is equal to the average velocity multiplied by time. And the average velocity, if you're accelerating at a constant rate from u to v, is going to be equal to u plus v divided by 2. So s is equal to u plus v divided by 2 multiplied by time. And that's the final velocity, usually actually written as s is equal to half u plus v divided by t. Exactly, yeah. So that one doesn't have an a in it, and so we've got all of the equations that we need. The only one I didn't derive was the one with that looks like s equals ut plus half at squared. So that was the s equals vt minus half at squared. I didn't derive that one. So you can imagine that, and so that's, let's label that equation 5 then. So you can imagine a SUVAT question now, where you have to like decide which of these 5 equations would we use. Maybe I could put it here. Let's just find a SUVAT question. So this could be an example SUVAT question. It's given us 3 variables. It's the initial velocity is 2, so we're saying that u is 2. Here we are. So u is equal to 2, and we've got v is equal to 10 meters per second, I should say. And we've got s is equal to 30. Now, I've not actually asked the question, so depending what question I ask would cause you to, to choose which one. So, but we've got 3 of the variables taken care of. The only one I haven't talked about is acceleration or time. So if let's say I want to know what is the time, then the equation I've not talked about is the acceleration. I've written, so the acceleration here. So we would use equation 5 because it doesn't have acceleration in my question and I don't have to work it out. So I'd use equation 5, but I would have to rearrange it. If instead I asked for the acceleration and I didn't ask for the time, then I want to use this one. And again, I'd have to rearrange it, but because it doesn't have time in it, then I could use u, v, and s, rearrange it to find out what a is. Does that make sense? So this is if you click here, this will take you to a SUVAT calculator, which is really cool actually, because it shows you the workings out and everything. So you can have a go at this question, and then, in fact, you can set your own questions as well, and then you can solve them with a SUVAT calculator. But it's just suvat.app, but it's really, really cool actually. So use that.